Locomotion control for quadruped robots using terrain-aware neural model switching between whole-body dynamics and reinforcement learning. In this paper, we propose a terrain-adaptive locomotion control framework for quadruped robots. To achieve this, we developed a curriculum-based reinforcement learning environment to obtain control policies that are robust to rugged terrain. At the same time, stable locomotion was ensured by computing optimal ground reaction forces through whole-body dynamics control. In addition, a terrain difficulty perception net was trained using the robot's proprioceptive state observations to estimate terrain difficulty in real time. Within the proposed framework, the robot applies dynamics-based control on low-difficulty terrain to maintain trunk stability. When the terrain becomes more challenging, it switches to learning-based control to preserve target velocity and overcome obstacles effectively. In this study, we implement a curriculum-based reinforcement learning framework to achieve stable locomotion on highly challenging, irregular terrain. The locomotion policy is optimized using KL-regularized proximal policy optimization. In this formulation, a Kullback-Leibler divergence term is incorporated into the standard PPO objective to ensure stable policy updates. To learn stable quadrupedal locomotion, we designed a group of reward functions that guide foot behavior during both swing and stance phases. The core idea is phase-based role assignment, where each foot follows a predefined swing or stance schedule. The scales and parameter values of all reward functions are summarized in table. We formulate a 6 degree of freedom floating-based dynamics model for whole-body control. For whole-body control, the optimization variables consist of generalized acceleration, joint torques, and task space ground reaction forces. The floating-based dynamic is imposed as inequality constraints within a quadratic programming formulation. The primary objective of the whole-body control framework is to compute optimal body accelerations and ground reaction forces through quadratic programming. The cost function is formulated using task space tracking objectives. A matrix constructed from the system Jacobian and a vector based on desired accelerations define the quadratic form of the optimization problem. Inequality constraints are introduced to enforce unilateral contact and friction cone conditions, ensuring non-slip interaction between the feet and the ground. Finally, the optimized accelerations and ground reaction forces are inserted into the inverse dynamics formulation, producing the torque commands executed by the robot's actuators. This block diagram illustrates the terrain difficulty estimation network and the proposed switching strategy between whole-body dynamics and deep reinforcement learning control. The core of the algorithm is a terrain difficulty observation value, represented as a single scalar. This value quantifies the complexity of the terrain currently being traversed. It is normalized with respect to the range of simulation terrains encountered during training. When the value is close to 0, the terrain is considered flat or low in difficulty. As the value approaches 1, the terrain is recognized as highly challenging, indicating a greater need for the adaptability of reinforcement learning control. To estimate terrain difficulty reliably, the perception encoder utilizes 3 categories of proprioceptive features. First, roll and pitch angles of the trunk. Second, terrain irregularity is captured per the vertical difference between the highest and lowest foot positions. Third, trunk dynamic fluctuation features are incorporated, including lateral and vertical velocities, as well as absolute trunk height. The 3 feature categories are combined into a single input vector. This vector is then organized into a fixed-length temporal stack before being fed into the perception encoder. The estimated terrain difficulty serves as the decision criteria for control mode selection. When the difficulty is below a predefined threshold, whole-body dynamics control is applied. When it exceeds the threshold, the framework activates deep reinforcement learning control. The effectiveness of the switching framework is illustrated in the corresponding figure. As the robot entered the difficulty level 4 region, the estimated terrain difficulty increased sharply at approximately 82 seconds. At this moment, the mode transition signal changed instantly from 0, representing whole body dynamics, to 1, representing reinforcement learning. This confirms that the robot correctly identified the increase in terrain complexity and adapted its control strategy in real time. After successfully traversing the 15-centimeter stairs and descending the slope, the robot reached flat ground at around 106 seconds. It then initiated a smooth transition back to whole-body dynamics control at approximately 108 seconds, completing the interpolation within about 2 seconds. The upper plot presents a comparison of trunk posture stability between the two control strategies on difficulty level 3 terrain. As observed in the simulations, whole-body dynamics control maintains superior stability on terrain that lies within its controllable range. In contrast, the lower plot shows the total joint torque consumption. Here, the reinforcement learning controller demonstrates improved energy efficiency when overcoming irregular terrain.